Okay, so welcome to this next video in which we are discussing the sinoatrial node. Okay, so far what we have discussed is that when the electrical potential difference across the cell membrane of a sinoatrial node cardiomyocyte gets to negative 70 millivolts, i.e. hyperpolarized, then what will happen is these HCN channels will open, and these are roughly equally permeable to sodium and potassium. If anything, they're slightly more permeable to potassium. However, which of these two permeabilities is going to be more important? So I've given you this data and I've given you the task of trying to work it out. So, potassium concentration gradient favours the movement of potassium out of the cell, because this intracellular potassium concentration is far greater than the extracellular potassium concentration. However, the electrical potential of the intracellular compartment is at the moment 70 millivolts lower than the electrical potential of the extracellular compartment. And potassium ions have a positive charge, so they like to be in the place where the electrical potential is lower. So they're going to want to stay in the intracellular compartment. So the electrical gradient is pulling the potassium back in. Now, it is true that the concentration gradient is stronger at the moment than the electrical gradient. In fact, to get an electrical gradient that will balance this concentration gradient, you'd need around negative 85 millivolts, which we don't have, okay? But it's nearly there. So the actual amount by which the concentration gradient is beating the electrical gradient is not that great, okay? So the driving force for potassium out is quite low, whereas the sodium concentration gradient is favouring the movement of sodium in. In addition, the electrical gradient, this intracellular electrical potential, is 70 millivolts lower than the electrical potential of the extracellular compartment. Sodium again is a positive cation, so it wants to move into the place where there's a lower electrical potential. So the electrical driving force is driving sodium in as well, so they're both driving sodium in. They're both favouring the movement of sodium in. So in fact, the driving force for sodium to come into the cell is far greater than the driving force for potassium to leave the cell. So really what's going to happen when you open these HCN channels is you're going to get sodium coming into the cell. Okay, now when you bring these sodium ions into the cell, that constitutes a positive current into the cell. You are bringing positive charge into the cell. Current is just the movement of charge. So this is a current across the cell membrane. And this current has a name, has a very important name. So this is what we refer to as the IF, okay? And it stands for the funny current, okay? So the movement of sodium through the hyperpolarization and cyclic nucleotide gated channel is the funny current that comes into the cardiomyocyte the sinoatrial node cardiomyocyte. Okay, so this movement of positive charge, that's what we refer to as the funny current, or the IF. Okay, now what is this IF going to actually cause? Well, we are moving positive charge into the intracellular compartment and out of the extracellular compartment. Positive charge raises the electrical potential of places. So if we're moving positive charge into the intracellular compartment, we're going to raise the electrical potential of the intracellular compartment. In addition, we've moved it out of the extracellular compartment, so that's going to lower the electrical potential of the extracellular compartment. Now, you remember me telling you initially that the electrical potential of the intracellular compartment was 70 millivolts lower than the electrical potential of the extracellular compartment, and that meant that the voltage from extracellular to intracellular was negative 70 millivolts. Now, if we're raising this one and reducing this one, then the difference, how much this one is lower than this one, is going to get smaller. So we're going to make this electrical potential difference across the membrane less negative. What we're going to do is we're going to see a depolarization across the cell membrane. So we're going to get a little depolarization like this. Okay? Right. Now, what happens is the electrical potential difference across the membrane depolarizes because we're raising the electrical potential of the intracellular compartment and reducing the electrical potential of the extracellular compartment. And what that is going to do is it's going to depolarize the electrical potential difference to threshold potential for another voltage-gated channel. This time a depolarization voltage-gated channel, so one that's activated by the depolarization rather than by the hyperpolarization. So this is a more normal channel. Okay, alright, so what's this next star of the show? So the next star of the show is, you're waiting for me to say a voltage-gated sodium channel. You're going to be disappointed, it's not a voltage-gated sodium channel, and this is really important to remember. This is different from in neurons, and it's different from in normal cardiomyocytes. The sinoatrial node is different. Okay, so it does not have a voltage-gated sodium channel responsible for the upstroke of the action potential. Instead, it has a voltage-gated calcium channel. Right, so this is a voltage-gated calcium channel, and it is specifically a voltage-gated calcium channel of the T-type. So I want to try and explain to you what I mean by a T-type voltage-gated calcium channel. VGCC is short for voltage-gated calcium channel. Okay, so basically, voltage-gated calcium channels consist of multiple subunits. Okay, so the most important subunit of a voltage-gated calcium channel is the actual subunit which forms the pore across the membrane. Now this subunit is known as the alpha-1 subunit of the voltage-gated calcium channel, and I'll draw it again down here. Okay, so we have this actual pore-forming subunit of the voltage-gated calcium channel, which is called the alpha-1 subunit of the voltage-gated calcium channel. Now, there are many genes in the human genome which all code for alpha-1 subunits of voltage-gated calcium channels. Now, all of these genes have slightly different sequences of organic bases and therefore code for slightly different proteins. However, the proteins that you overall get are similar enough and have a similar enough function to all be grouped together as voltage-gated calcium channels. So, the number of genes for alpha-1 subunits are 10. We have 10 genes for alpha-1 subunits, and we group these into 3 major families. So there is the CAV1 family, which stands for voltage-gated calcium channel first family. There is the CAV2 family, which stands for voltage-gated calcium channel second family. And there is the CAV3 family, which stands for the voltage-gated calcium channel 3 family. Okay, now the first family has 4 genes in it, the second family has 3 genes in it, and the third family has 3 genes in it as well, so that makes overall 10. Now the 3 genes in the CAV3 family are cunningly named CAV3.1, CAV3.2, and CAV3.3, which is nice and easy. Okay, and these 3 genes are all coding for alpha-1 subunits, and if you make your voltage-gated calcium channel out of one of these 3 alpha-1 subunits, okay, so if you use one of these 3 genes, either CAV3.1, CAV3.2, CAV3.3, to make your alpha-1 subunit that you're going to use in your voltage-gated calcium channel, then the voltage-gated calcium channel you produce will be a T-type voltage-gated calcium channel. So basically, voltage-gated calcium channels are named after which alpha-1 subunit gene you use. And if you use one of these 3 that are in the CAV3 family, then you are called a T-type voltage-gated calcium channel. Okay, now voltage-gated calcium channels don't just consist of the alpha-1 subunit. No. They have a bunch of other accessory subunits which also stick on and join the fun. So here's another subunit here. So we'll draw these accessory or auxiliary subunits in. So here's the gamma subunit. Here is the beta subunit. And here over on this side is the alpha-2 delta subunit. So this is alpha-2 delta. Right, so let me colour in these different bits. So alpha 2 delta we'll do in blue here. Okay, so there's alpha 2 delta. Beta we'll do in orange down here. So this is beta. And gamma we'll do in green over here. Right, and these accessory subunits, they aren't part of the actual pore. The pore is formed by alpha 1, and if you just have an alpha 1 subunit on its own with no accessory subunits, it forms a perfectly good voltage-gated calcium channel. However, these other subunits modulate its function. Okay, so this is the structure of a voltage-gated calcium channel, and I've now explained to you what it means to be a T-type voltage-gated calcium channel. It means that the alpha 1 subunit is one of these 3 genes. Now, why are these channels which are built out of these 3 genes called T-type voltage-gated calcium channels? Well, basically, T stands for transient, and this reflects the fact that they open for a very short period of time. Now, all 3 of these alpha 1 subunits have a very important property, which is that when you depolarize a membrane, they will be activated to open, okay, and they will open extremely fast. So they open extremely rapidly, instantly almost, but they also close very fast. So that's why they are called transient voltage-gated calcium channels, or transient type voltage-gated calcium channels. And they have very different properties to the voltage-gated calcium channels where you use CAV1 and CAV2 family genes for your alpha 1 subunit. Okay, right. So back up to the picture. This is our T-type voltage-gated calcium channel. And basically, when you get to this negative 60 millivolts across the membrane of this SA node cardiomyocyte, it will activate this T-type voltage-gated calcium channel here to open. Okay, and we've only shown the alpha 1 subunit here. I might just add in the auxiliary subunits just for completeness. There they are. Okay, so this channel will now open. Now, which way is it going to allow calcium to move? Well, I'll give you another few clues to help you on this. Right, so the calcium concentration extracellularly, which I'll write here, is 1.5 millimolar, or thereabouts, which looks pretty pathetic when you compare it to the sodium and potassium concentrations. But then, look at the concentration of calcium intracellularly. It's 100 nanomolar. Okay, now look at this gradient here. That is a 15,000-fold gradient. The concentration of calcium extracellularly is 15,000 times bigger than the concentration of calcium intracellularly. That is massive when you compare it to the miserable little 12-fold gradient of sodium and approximately 40-fold gradient of potassium. So this is a powerful gradient, and we'll continue this discussion in the next video.